This is part 2 of Unit 7, Lesson 4, Newton's Law of Cooling and Logistics Functions. In part 1, we did logistics functions, so we're going to tackle our final differential equation, which involves Newton's Law of Cooling. So this law states that the rate of change in temperature of an object is proportional to the difference between the object's temperature and some fixed constant B, which is the temperature of the surrounding medium. So here is what the form of both the differential equation looks like. So it looked like K times Y minus B. And then here is our general solution, which looks a little different than what we're doing with regular exponential growth and decay. But still, the same laws apply. If K is greater than 0, we have growth. And if K is less than 0, we have decay. So if something is warming up, K should be positive. If something's cooling off, K should be negative. So you're going to notice that most of our K, since we're talking about Newton's Law of Cooling, is going to be cooling off. But sometimes we heat things up, so K will be positive. Okay, so typically you use this when we're talking about, as we said, Newton's Law of heating and cooling. If objects are falling and they're nearing terminal velocity, and if you're deflating something and finally the pressure inside is not enough to sustain the shape, so the outside pressure dominates and takes over the inside pressure. So let's go through one example, and we'll go from here. So example 3 says you bought your favorite frozen coffee treat on the way to school at a drive-through window of Starbeams. Your car is always kept at a constant 65 degrees Fahrenheit. Traffic was terrible and you spent 10 minutes getting to school. The drink warmed to 35 degrees Fahrenheit because you checked it with your temperature probe at the red light, because everyone has one of those in their car. And then 2 students had a rear-end collision in the parking lot, and another 10 minutes passed trying to get in the school parking lot. You checked your drink again and it warmed to 50 degrees Fahrenheit. So we're to use Newton's Law of Cooling to estimate the following original temperature of our coffee drink first. So we're going to start with our differential equation, which is dy dt is equal to K times Y minus B. And remember that in this case, our B is 65 degrees because that's what our temperature of our car is. So we have dy dt is equal to K times Y minus 65. Okay, now we're going to solve our differential equation. So we're going to have dy over y minus 65 equals the integral of k dt. So integrating this, we get the natural log of y minus 65 is going to equal kt plus c. Okay, taking the natural log of both sides and simplifying the right-hand side the way we know it does with differential equations, we're going to have y minus 65 is going to equal a e to the kt. Now what we're going to have to do is use our 2 initial conditions, or not initial conditions, our 2 given conditions to find a and k, because we have a and k, because we have 2 variables. So what we know is, and let's go up here, what we know is that when t equals 10 minutes, our drink's temperature was 35 degrees. And so substituting that into our equation, we're going to get 35 minus 65 equals a e to the 10k. And the other condition is we know that another 10 minutes passed, so that's 20 minutes in total. Our drink was now 50 degrees. So that'll give us 35 minus 50 is equal to a e to the 20k. Now we did this in lesson 3, how to solve this, and since we're talking about multiplication, we are going to use division to help us solve this. Let me just simplify these real quick here. So this will be negative 30 equals a e to the 10k, and the other one becomes negative 15 equals a e to the 20k. So I like to have my bigger exponent on top. So I'm going to do negative 15 over negative 30 is equal to a e to the 20k over AE to the 10K. So that cancels out that variable for now. So I have 1/2 equals E to the 10K. And then solving for K, take the natural log of both sides. I'm going to get ln of 1/2 equals 10K. So K is going to equal ln of 1/2 over 10. And I'm going to leave it like that for now. Okay, now that I have K, I'm going to go back and find, I have K, I'm going to go back and find A. So I'm going to use my negative 30 equals AE to the 10K, because I have a 10 to cancel out there. So I have negative 30 equals A times E to the 10 times ln of 1/2 over 10. And this is why I wanted to leave it in the ln form. So these will cancel. So I have negative 30 is going to equal, those are inverse operations. So I'll have A times 1/2. And then solving for A, I get A equals negative 60. Okay, so now I have my equation. So I have y of t is equal to negative 60 e to the ln of 1/2 over 10t, and then I have a plus 65. Now I can find my initial temperature of my drink by just substituting 0 in, so that'll be e to the 0 plus 65. So I will get that it was negative 60 plus 65, which is 5 degrees. So there's part A. Okay, next, part B. When will the drink reach a temperature of 63 degrees Fahrenheit? And that's just a matter now of solving each of these. So I will let you guys do those, and I am going to write the answers here for you. So the answer to part A is going to be T equals 49.0689 minutes. And for part C, you should get that this is approximately a temperature of 64.062 degrees Fahrenheit. And pause the video and do the problems. And if you have trouble getting the answers, we'll go over them in class.